Okay, so today is about data analysis and visualization. And these are two topics that are, both quite diverse in a sense. There are a lot of ways to analyze these data. And we've talked about several of these things already during the earlier lectures, but I wanted to try to summarize it here. And they're also very much interconnected, that it's always good to try to visualize the data in a good way while analyzing it, to come up with maybe new ways to analyze it, but also to make sure that the analysis makes sense. And the visualization part is inherently difficult because the data is so rich and it has so many different aspects that to do the visualization in a good way is not really straightforward. So when it comes to the data analysis, so the basic statistical approaches that are used are a lot of them are quite well discussed in this blog, which is so this is a series of short articles on different aspects of statistics that are definitely worth looking at to give you a good background. And the articles are nice, usually 1 or 2 pages, and discuss one topics, and also usually goes into what the problems is of that. And so that's and the other blog that's available is one on visualization, also from Nature Methods, that I recommend, where they talk about all sorts of aspects of how to visualize data, starting with what colors to choose and these and basic things, but also then to more advanced visualizations. So as we looked at before, so one aspect that we in data analysis we have to do is to identify the proteins that are in our sample, and the idea there is to try to use the data so that we can identify as many as possible without getting a lot of just random matching. And so what we do practically is that we try to mimic the experiment. So in the experiment we first prepare our sample, digest the proteins, and then separate the peptides, and then measure lots of MSMS spectra. And then we mimic this in the computer, where we take a sequence database, pick a protein, digest it, and then pick a peptide, then calculate all the possible fragment masses, and then finally compare the peptide. And then we calculate the score and test significance. Then we repeat this for all peptides and for all our proteins in the database. And then we do this comparison for every spectrum that we've measured. So it ends up being a lot of comparisons, and then we always have of course, a finite mass accuracy. Even though it can be quite accurate, it's still not perfect. And we also have that the different amino acids are built up of the same atoms and a small set of atoms, like carbon, hydrogen, nitrogen, oxygen, sulfur. So they are going to be the masses are different for most of them, but when we try to sequence, there could be a lot of confusion since we usually don't get complete fragmentation. But when we do the scoring, and we always pick the one that matches best. So that can be the statistics behind that is what's called we're looking at the extreme value, so the highest score always. So if we do this for a so then we get the search results, and then we want to assess how much we can trust this. So the statistics is the extreme value statistics, since we pick always the highest score. So the way then that we want to determine when is this just a random match, or when is it really a true match. So we need to develop an objective criterion for how to test the significance. And what we need to know is what the score distribution is for false results, and then we can from that estimate what the chance that our score, the spectrum that we scored has is just a random match. So what happens if we look at extreme values? So now this just shows examples of two distributions, one normal distribution and one skewed distribution here. So below here what we've done is that we've randomly picked, in this case, 3 values from the normal distribution, and then we select the maximum of those 3. And the distribution then of this looks as plotted here. So what you see is that, of course, since we picked the distribution has shifted away from 0, so it's not anymore centered around 0. And this might be a little bit difficult to see, but it's a log scale. Here. So what we see here then is that the tail is an exponential. So it's can be pretty well approximated with a linear function when we plot it on a log scale. And so what happens then if we take randomly pick 10 values from this distribution and take the maximum of that? We again have more of a shift towards higher values, but still an exponential tail. And then here in this case 100, we again get a larger shift, but again exponential. So then if we do pick from a skewed distribution, we see the same trend. As the more values we pick and select the maximum, of course the further we're shifted. But what we see is that the tail here is quite linear on an exponential curve. And so we can use this fact that for quite a wide range of distributions, if we pick the extreme value from a set of when we pick a sample, and then that sample select the largest value, that the tail of the distribution will be exponential. So for some scoring algorithms, like for example for BLAST, one can actually show it in a formal way that we have an extreme value distribution with an exponential tail. Now no one has actually shown it for the mass spectrometry scoring algorithms, but when one looks at it, looks at the results, it looks very much that in in a lot of cases we get an exponential function. So here is one example that we looked at earlier, where we have a distribution. We have, in this case, this is for peptide mass fingerprinting, so we have 2 high scoring proteins, and then a distribution of low random matches. So this distribution then, so if we put it on a log scale instead, we can see that it's, now the statistics is not great in this case, but if we make the assumption that it follows an extreme value distribution with an exponential tail, we can extrapolate and calculate what the expectation value is for these high scoring proteins. And so the interpretation of the expectation value is that for low scores, that's the number of proteins that we expect to find at that score at random. And then when we go to values below 1, then it's the probability that our match at that score would be random. So this is, again, one can, for any scoring algorithm, one can calculate an expectation value. So it's done for BLAST, which is the most famous one, but you can also do it for any and it's done quite a lot in proteomics for a wide variety of different algorithms. Then other methods to estimate what's the how much one can trust the results also include using decoy databases. And we've talked a little bit about that earlier. And there, what one tries to do is one creates a protein sequence database that is similar to the one that one has, the real protein sequence database that one searches, but it doesn't contain any real sequences, preferably. So one way, probably the simplest way, is to reverse all the protein sequences and then digest them the same way, because then almost none of the sequences will be matched the real. There will always be a few, of course, but the distribution, the number of peptides, the length distribution of peptides will be the same. So that so that way, if we search that, all in addition to searching the regular sequences in the database, we can get an estimation of what random matching the random matching contribution is. And then we can estimate the false discovery rate. So we can estimate, if we set a certain score cutoff, we can estimate how many incorrect identifications we have. And this is probably the most widely used way to do it, because it's very simple to implement. So this was about identification. So here the main worry is how we distinguish random from non-random identifications. And then finally, when we have this distribution of random and false identification, then we can assign either expectation values, or we can set false discovery rate cutoffs. So the identification is just the first step. So the next step that in most experiments that we're interested in, of course, is to do quantitation. So here we discussed a lot of different ways to do quantitation, either by not using an stable isotope label, or by using a stable isotope label and introducing it at different stages of the experiment. And we discussed a lot about the different drawbacks and the different advantages of the different methods. But in the end here now we measure a quantity. And so there, if we do a measurement of a quantity, then we need to find a few things. We need to find the limit of detection. So here, this just shows one example where we have done a titration curve. So here we have the theoretical concentration over 4 orders of magnitude. And we see that in this case, we get a very nice linear response between linear relationship between the theoretical and the measured concentration. We get a little bit of variation, but it looks very good. But then at some point, we run out of steam when we go down in concentration, and we can't measure the concentration well anymore. And this is very typical how it would look like. So we want to determine this limit of where we can really start measuring and start having a linear response. So there are a few things that people talk about with analytical measurements, and one is accuracy, of course. And so accuracy is really how well what we measure corresponds to the real concentration. Then another thing we talk about is precision, and that is how reproducibly we can do the measurement. So here, this little figure shows what. So we have the reference value, and so the accuracy is how far we are from that, and precision is that if we do repeat measurements, how big of a spread we get around our measurement. Then robustness is also about how well, how much does our measurement depend on when things that we can't really affect change, like does it matter how we store the sample? Does it matter how much time is between when we take it out of the freezer until we measure it? And all those things that you can think of that one can't always control very well. And then we talked about lower limit of detection, and that is when we can start distinguishing from a blank measurement, and that is usually lower than the limit of quantification, and the limit of detection is really when we start seeing a difference. But limit of quantitation, we want it to be that we have it within a certain precision and accuracy. So as you can imagine, if we'll go back here, here right above, when we start detecting it, the variation might be quite high, because there is still a lot, much larger contribution from background. And then the linearity, that's very important. And in a lot of times when we talked about quantitation, the linearity was assumed implicitly, but we actually didn't. Usually, we don't actually test what is the lin. But to do a proper analytical measurement, one should know all these what all these numbers are, and so that one can really trust it. But of course, in the case when we do discovery proteomics and look at many measurements, we don't actually do establish these values for all of them. But in one case that you heard Kelly talk about, when we do targeted measurements, then we actually usually do these things properly. So then the one thing about measuring, so the one question is, we always like to prefer to make assumptions about that things are distributed normally. But in the case when we measure blanks, then usually that assumption is not valid. So if we could put the zero level accurately, we would actually only measure the ones that are higher than zero. So we would have a half a Gaussian. But we actually don't always know how to find the zero level. So we can have different cases where we just have these different distributions, and the gray areas we don't see. So actually, assuming that the blank measurements are normally distributed is probably a bad idea in general. The other thing that we usually like to calculate for the measurements is the coefficient of variation, which is just simply the standard deviation divided by the mean. And this is now when we measure for the values for the non-blanks. And of course, this would best is if there is a normal distribution. If we sort of implicitly assume that, because then the mean and the standard deviation are better defined. Now, if we look at how to estimate what the lower limit of detection is, there are a few different ways, but if we'll just look at two methods to do that. One that people usually use is that just taking where the coefficient of variation is less than 20%. So that would be the one way of defining it. Another way is, which is probably much more robust, which is described in this paper here, is to measure the level of the blank by doing repeated measurements and then taking the 95th percentile of the blank measurements and then adding a constant times the standard deviation of the lowest concentration. And this is probably the best way to do it rigorously. But of course, here now we have to make many measurements of the blank, and preferably maybe 10 or 20 measurements of the blank. So again, if we're doing this, it definitely will require quite a big effort to do this. So then the limit of detection, so we talked about that. So that's what's shown here. So the lower dotted line is the limit of the blank calculated from these cases, and the higher up, the line that's a little bit higher up, is the limit of detection. And then we have now, in this case, the linear range. So another thing that can happen is also at high concentrations, we might have a saturation. So we have the linear range just for some span. And that also depends on how we are measuring things, but it's not unusual with mass spectrometry. If we have very high amounts that we see a saturation. And then this is just another another example. So here we have a measurement that's both accurate and precise. While here we have a measurement that has about the same precision, maybe a little bit lower, but it has a much worse accuracy. Because so the solid line here is the theoretical, what we should have. So now, if we look at two data sets. So we measure a lot of proteins, and we measure them twice. So these are two different samples. So actually one is a basal tumor and the other one is a luminal tumor. So now we're showing this on a linear scale on both, and we see that most of our data is here, and there are some that are very high abundant. So usually it's better to show this on a log-log scale. So here we can see much better what's happening, that we have a lot of the proteins are very similar. So this is now spectral counting data. So that's why you see at low counts, you see that it's discrete points. So this is because it's integers that we're counting. One thing that we can do then, which probably makes it easier, is to turn this. Oh no! So the other thing that we have is that in this case, since we moved to a log-log scale, we lost the ones that were 0 in one of the samples. So now, in this case, we've added them back to an arbitrary position just to show them, but they really should be. So we should, in this case, we try to put them just very close to the axis at 0. That's important. And we see that in this case there are quite a lot. And even though there is, it's quite a high spectral count in one, but not 0 in the other. So the other thing we can do is to, instead of showing one sample against the other, we can show the ratio on the x-axis and the sum or average on the y-axis. And then we see that we have and then again, now we've placed these at, or the ones that are 0 spectral counts, we place them at an arbitrary location. We put them at 10, at n minus 10. And these are the ones that are along here. And then we can show this as a histogram. So now, of course, we need to think about how. I mean, there are a few things. One is, the question is how well how similar are two data sets? Before we even start looking at what is different, sometimes it can be worth looking at how similar they are. So if we actually, sorry, that comes a little bit later. Let's look at this first. So this is another example of a sample now, of two samples that are compared, and we haven't, in this case we have just done two measurements, one on each sample, no replicates. So the question is then, how do we decide which ones are significant, which ones are different between the two samples? Now, so we can't do any statistics, we can't do a t-test because we don't have replicates. We just have one measurement for each sample. So one thing we can observe here is that depending on the intensity, we have that the distribution is wider at low intensities and gets narrow at high intensities. So what we can make some assumptions on this and look for outliers. And that's probably, in this case, if we don't have any replicates, the best we can do. But of course, that's not so reliable. So now we have another case where we have 3 replicates. And now we have done a t-test, and the ones that are red are the ones that are significant from a t-test after a multiple testing correction. And it might be a little bit difficult to see, but you see quite a few of the gray points that are still quite far away from this. There's one here, here that are surrounded by significant, but they are not significant even of. So the one where we make the assumption about the distribution and look for outliers is definitely a very dangerous thing, especially since if we compare it, now this is just picking one pair of replicates from these 3. We see that we have a much wider distribution, and definitely if we would have just picked outliers, we would have gotten a lot of them right, but maybe half of them wrong or something like that. So quite a lot. So it's definitely not advisable to not do replicate measurements. But the problem is that sometimes it's expensive, it takes time, so people try to avoid doing it.
I have a question.
Yeah.
For the y-axis, the first plot, for the y-axis, the sum spectrum count, is this the sum of 2 conditions of all the replicates?
Yes. So it's first we average within each condition, and then we take the sum of the 2 replicates. But we could have equally taken the average there also. That would have worked fine. So instead of, so it doesn't really matter if one takes the sum or the average on the y-axis.
Then isn't it like less informative if we mix 2 conditions in a sum scale?
Yeah, I mean, yes, you mean that if in one case we have a very low, yeah. No, that's but the idea here would be that one both wants to separate it according to ratio, and then it's just a visual display that we also want to have it separated according to the intensity. And that's why in this case we took the sum. And of course, it will work best for the ones that where it's similar. But it's just so that we can separate the points in 2 dimensions, really. And so then, if we go talk a little bit about how different are 2 measurements. So here there is scale, it says CV here, and below it says shape. So CV is 0.4. Sorry about the contrast. So the CV is 0.4 in this case, so the variation is 40%, which is quite not very good. And then here the shape factor, which determines how skewed the distribution is at 3 in this case. So now we get, if we do a correlation, calculate the correlation coefficient, it's 0.63. So now, of course, if we improve the CV, so the lower the CV, we're going to get a better correlation coefficient. So if we do this, for example, here, if we move it down to the CV to 0.1, we see that the data is much better correlated, and we get a correlation coefficient of 0.097. 0.97, sorry. But even if we keep the CV at 0.4 and now instead lower make the distribution more skewed, we can improve. We can get to so now the quality of the data is the same. So the coefficient of variation is still 0.4, but now we have made this distribution very skewed. So which is so we have most of the points here, but we have some outliers. Then we can get a correlation coefficient of 0.97 again. We do this all the time to compare measurements. We calculate correlation coefficients, but it's not the best way to do it. Because one can, and you see that, I don't know if you remember, but this is not very different from what we saw when we plotted our comparison on a linear scale. It was, I can go back to, so you see here, in this case, when we plotted on linear scale, we have most of the points here. So if we would calculate the correlation coefficient of this, it would probably be quite decent, just because it's so skewed. So that's something to think about, that you can pretty much, depending, if you decide on the CV, you change the shape, you can get any correlation coefficient you want. So now, if we look at the different data sets, so now we have 7 samples and 3 replicates each. So what we've shown here is the now the log2 intensity on the x-axis, and then the number of proteins on the y-axis. So we see that the 7 measurements are quite similar. We have a little bit of variation here, a little bit of variation there, but in general it looks quite decent. We also observe that it's not in this case a symmetrical distribution, it's slightly skewed. So what we can do is we can normalize it, and the way we would normalize this, or one way, is to make all the medians the same, or the means, but usually it's better to choose the medians, and then we make the standard deviation, set that to 1 in this case. So then we get and you see that they align much better, but not perfectly. So now in another case, so we had these 3 replicates, but then one more replicate that was collected a month later. And then the response of the instrument was slightly lower. We see these here. There's actually one of them over here, but most of them are down here, where we get lower intensities in general. But if we apply the same normalization, we can see that we get a pretty decent, they all line up very nicely. So this is something that one should always look at. And this is pretty standard in all sorts of measurements, like in microarrays, RNA-seq, and all sorts of, and also in proteomics, one should. And it's also, I would definitely recommend both doing this normalization, but also looking at the data both before, in this form, both before and after. So the way that these curves are constructed is that it's what's called a kernel density estimate. So for each protein, we put a small Gaussian distribution and we add them up, and then to be able to get these smooth curves. An alternative would be to do a histogram, but in general, it's much easier to work with a smooth curve, especially if we want to compare many of them. So now we looked at correlations before. So now this just shows that even if we have a larger data set with 7 samples, we can compare them pairwise. And also see how, and it's often quite useful just to get an overview of what's going on, to show all the plots at the same time. And then one thing we can see, for example, here we have a very nice correlation. But if we look at these 2 samples here, we see that most of them correlate, but then there is something going on, and that might be worth looking at what's going on there. So we can get a quick overview, and we can assess the quality and so on with these plots. So then now this is just the same data, but now instead of comparing directly the intensities, we're looking at, again, the ratio on the x-axis and the sum on the y-axis. And in this case, we have actually the points that are marked in red are the ones that we deemed to be outliers. You had a question?
Yes. So for the outliers, they are like they have some complication in one sample, but not in the other sample. So
yeah. So that's the extreme outliers, but there are. I mean, it might be a little bit difficult, but like there are ones marked in red here also, okay, for example. So we're looking at outliers. So usually in this case, what we use the non-parametric one. So we look at the median and then the interquartile range to estimate what's an outlier. So another way to display data that's very powerful is a box plot. And I don't know, you probably have used that already quite a bit. But the idea is that in a compact way, we can show quite a lot of information. So here we have an example with just 20 points that are shown, and usually we show the interquartile range as a box. So that's Q1 to Q3. We then show the whiskers go out to 1.5 times the interquartile range, and then any points that are above there, we show the actual points as outliers. And then one can, so this is then the mean is shown also, and one can add this notch for the confidence interval also. But that's not always necessary. So just a few examples. So if we have a normal distribution, and now we just pick either 5 points at random, 10 points or 100 points, these are the box plots that we would get. And you see here we just get an occasional outlier in these cases, but usually not. So if we have a skew distribution, of course, we have much more outliers. And also so we have, if we take a distribution with a long tail, then you see here we have lots of outliers. In skew distribution, we of course have the outliers in one direction. And then we have a very strange distribution here. We get, of course, very large boxes because it's a very large distribution. So another thing we can do with the box plot is that not just show the outliers, but show actually all the points, which I definitely would recommend if you don't have too many points. So here, for example, we show, now it's a little bit difficult to see maybe, but it's, even if we have, in the case of 100 points, it's nice actually to show all the points in these cases, because we can definitely learn more by seeing the actual data. So there are a few different ways to show the results. So here, if you have a normal distribution and we have now different steps. So here we show the results with a bar graph with either error bars at the standard deviation or as the standard error, which is of course much smaller. Or if we show it as a scatter plot, where we show the value, the mean, and then the standard deviations. Or if we show the box plot, either just with outliers or with all the data points. So in this case, what we didn't see from the other places, if we show all the data points, we see that we have many more points, measurements here than for the other ones. And I mean, definitely, I think this is very valuable to see that how many, especially in cases when there is such a big difference between the different, the number of measurements in different points. So now this is just show the same thing for a skew distribution and for the distribution with the long tails. So now we go to talk a little bit about other visualizations. So one thing that can be very nice is to show Venn diagrams. But usually there are always tools that generate Venn diagrams automatically. But if you want to do a Venn diagram like this for a figure for a paper, you have to do it manually. Otherwise, the automatic tools will not do it usually very well.
Manually by which kind of program?
Illustrator, for example. I mean, you can use PowerPoint also, but Illustrator probably. This one was done in Illustrator. But you can first generate it automatically and then fix it up. So now it's the question of how do we deal with these large data sets? How do we show when we have lots of samples and lots of measurements? So this just shows for the TCGA breast tumors, it shows the expression analysis. And so heat maps is one way to, in connection with clustering, is one way to show how make sense of large data sets. So in this case, we have the samples here on top, and then we have the different genes, and a few of them just highlighted, but there are lots of them. And then underneath here, we have annotated it with other, like the PAM50 status, ER, PR, HER2, and so on. So this can often be used to summarize a lot of information. So we talked a little bit about correlation between different, I mean, we talked about correlation between the same measurement in different samples. But we can also do different measurements and correlate those. So this just shows the correlation between mRNA and protein in 95 colon tumors. And we see that we get for each of the proteins that were measured. So these were, I don't actually know how many proteins, but the ones that had both an mRNA measurement and the protein measurement. And as you can see, the correlation is as usually measured in a lot of different tumors, in a lot of different contexts. It's around 0.4 on the median.
Sorry, does that mean that for the record has low correlation scores? Does that mean we don't have like a measurable amount of mRNA and proteins?
No, so these were the only data that was included here was the ones where there was measurable amounts of both. So the ones where either, I mean, usually mRNA is measured for almost everything where we have protein measurement, but not all of it. But those were, when we don't have a protein measurements or no RNA measurement, those were removed. So these were the only ones where both measurements were non-zero. And still, I mean, but the correlation is, but if you look in detail at these correlations, so now this is from the same paper, it shows now on the x-axis here, it's copy number. So it goes from here is chromosome 1, 2, 3, and then all the chromosomes lined up. And then this is gene expression, also in chromosomal coordinates. And then protein. So this is again copy number, but the y-axis here is protein amount. So what we can see is that there is quite a lot of correlation between copy number and gene expression in the same location. And then, but there are certain locations where a copy number change leads to changes all over the genome in gene expression. So these the things along the diagonal are called the cis effects, and then these stripes are the trans effects, where one copy number change affects a large number of genes. And then we see much weaker, but we see similar things for the protein analysis, from the protein copy number correlation. So we can definitely see. So these are just different examples of how we can try to also expand beyond just visualizing the proteomics data to comparing it to other data types on the same sample. And this is yet another example. So this is for HER2, looking at, in this case, 80 breast tumors. And we're looking at, for HER2, the copy number changes here, done here in purple. Green is the mRNA, and looking at now outliers, and then protein outliers in yellow, and then if they're not outliers, it's in gray, and then these are different phosphosites. So it's shown more in closer here, and actually showing each distribution, and when there are outliers, they're colored. So what we see here is that this pink here are the HER2 positive, HER2 amplified tumors, and we see that it's mainly there where we have a copy number change that leads to both an mRNA change, protein change, and phosphoprotein change. So this is another way to look for correlation between different data types. So now, just a final thing about multiple hypothesis testing. And we've talked about this a little bit, but when we do a lot of measurements, we have to correct our p-value. So so we can ask two different questions here, for example, of a data set. So if we ask a very targeted question, for example, is the concentration of calcium calmodulin dependent protein kinase type 2 different in two samples? Then we do measurements and we calculate a p-value. And then that's what we can report at. But if we ask a more general question, what protein concentration was different between the two samples, then we need to correct because we're now making many tests. And and this multiple testing is actually a quite straightforward concept. It's the same thing as when you buy a lottery ticket, the chances that you win is really small. But yet almost every week someone wins. So it's not a difficult concept. So there are a few ways to correct. Actually many ways. We'll just talk about. So the Bonferroni correction is that you just multiply the p-value with the number of tests performed. And this works pretty well if you only do a few tests. But it's a very conservative correction. And usually in clinical medicine, if a few things are tested, then you would could apply the Bonferroni correction. But in so this is just one. So example, if we had the p-value here, but then we measured almost 4,000 proteins, then we multiply the uncorrected p-value with the number of proteins. And in this case, we see that we still have a significant p-value. Now, if we look a little bit at how p-values are distributed. So now this is just a simple simulation of where we generate data and we do t-tests. So the sample size, we assume we have a normal distribution that we generate from. Our sample size is 10. So we're going to generate 10 samples in the sort of we generate twice 10 samples and then we do a t-test. That's all we're going to do. And we do this many times. And we plot the distribution of the p-values. So if we have 100 tests, we get, so this is a histogram, and we have 20 bins here. So we're going to divide these 100 into 20. So as you see, it's roughly around 5. If we do 1,000 tests, it's going to be roughly around 50, and then 10,000 tests around 500. So our significance test here now is on the first. Usually, if we select any p-value that's less than 5%. So if we have done 100 tests, we're going to have, in this case, 4. In this case, 42 maybe, and in the case of 10,000 tests, almost 500 that have a significant p-value before if we wouldn't correct. So that's the another way to look at why we need multiple testing. Because so that's the bin where that would be considered significant if we have a 5% significance value. So now we're gonna do a different simulation. So we're still doing the black curve, black distribution is the simulation that we did last time. We just redid it again, so the values are slightly different. But now we're going to select that 30 of the tests are have a different mean. So 30 out of 100, 30 out of 1,000, and 30 out of 10,000. So we see if we have 30 out of 100, we see that we get many more significant ones. So we've chosen that this so that it's much larger than the difference between the means are much larger than the standard deviation. So we're going to get all of those are going to be significant. So here in this significant bin, we're going to get the 30 plus any number of random ones. So in this case, we got 34, I guess. And then, but again, we can use this black curve to estimate the false discovery rate. So we would, in this case, take 34 divided by 6, I guess, in this case, to see what's the. We divide 6 by 34 to get the false discovery rate. And then, but as we increase the tests and we still have just a few, we still keep 30 are the ones that are really significant, we get a higher and higher false discovery rate because we get more and more random low p-values. So then we can, of course, plot this in a different way. So just plotting what the false discovery rate is as a function of p-value. And as we go up, the false discovery rate goes up. And as we have many more tests, we get higher and higher false discovery rate, even at low p-values. And we can also then look at the false negative rate. So the false discovery rate will go up, and then the false negative rate will decrease as we go up. So as we set, so if we set a very stringent p-value cutoff, we're going to have few false hits, but we're also going to have almost miss all of our the real ones. So that's why we have to find some kind of trade-off between when to, and of course, if we have the bigger the difference, the better we'll do on that. Then if we have a large difference between the means, we still get quite okay false negative rates at when the false discovery rate is controlled at some at a low level. So this is just some discussion, but it's really what the main thing is, that if we test many times, we're going to get randomly low p-values, and that's going to cause problems. So if we can have a very specific hypothesis and ask some question about just a few proteins, then we're much better off in general than if we ask open-ended questions like, what's the difference? So that was what I had for today. Any questions?